Good afternoon, everybody. I'm Neve Gibbons. I'm from the Department of Engineering at the University of Cambridge. I'm actually here today in lieu of Paul Fanning from University College Dublin. I did my PhD research with Paul a number of years ago, and Paul was involved in this UIC work group, and the way that I became involved in the work group was towards the end of my PhD. Paul said to me, "Oh, I have a little something that could make your thesis very interesting, and it shouldn't take too long." So this was half true. And the work that I undertook as part of that for the work group is actually something that I'll discuss in a bit more detail during one of tomorrow's sessions. And what I'm going to focus on now is some finite element modeling. I think on the agenda it's sort of listed as finite element and discrete modeling, but I'm just going to stick to the FE work instead. So finite element modeling for structures. Generally, it works quite well when the geometry is very well defined, when your material properties are well known and well understood, and when the loading and boundary conditions are clearly defined. So, with respect to masonry arch bridges, all of these are particularly challenging. So you come in for quite a lot of guff modeling masonry arches using an FE approach. And it really does require quite a bit of caution and care. So there's various different levels of complexity that you can take if you're adopting a finite element approach, both to masonry arches and to other structures. There's a bit of a summary in the guidance document that was the output of the work group in relation to these and obviously all of the other methods that are covered in this session. But essentially, you can adopt one-dimensional approaches as well, but generally these days most people adopt either a two-dimensional or a three-dimensional approach. With the two-dimensional approaches, you're neglecting things like the transverse capacity of the barrel, so you're sort of losing out on that distribution that occurs in the barrel, and you're also then possibly missing out on assessing the transverse capacity if you actually have a very weak arch in the transverse direction. So those are sort of main shortcomings of taking a two-dimensional approach. You can then sort of opt for either a linear or a nonlinear approach, speaking very, very broadly. With the nonlinear approach, the three-dimensional nonlinear approach is what I'm going to focus on in this presentation. This is really something that is much more time-consuming and computationally expensive. Matthew mentioned how Ring is slightly slower than Archie. You probably wouldn't even notice it. These models are the sort of thing that you leave running for a number of hours, and you might babysit using remote access to sort of check in on it every hour or so and look at how the convergence criteria are getting on. So they're not for routine assessment. You couldn't apply them across your bridge stock. It tends to only really be justified for more complex structures or more complex problems. Generally, it's where you have a very challenging problem, and therefore you're taking a more time-consuming and challenging approach. And really, from our own experiences in UCD, this does require a certain amount of model validation, and therefore for test data to go along with it. Like everybody else, I have results showing our wonderful correlation with our FE work that we did before the tests were carried out, and it all looks quite nice. But then when you dig into it in a bit more detail, you learn all sorts of things about your modeling approach and how you need to adjust it, and you really just can't do that without the field data. So at UCD, we've tested 8 different bridges out in the field. As other people have alluded to, there's pre-existing test data carried out at the Building Research Establishment and the Transport Research and Road Laboratory, and for other research projects. And much of that test data is very, very strongly focused on recreating two-dimensional conditions in some capacity or other. So sometimes that's very, very directly looking at a sort of a unit width arch with all of the sort of other elements stripped out, or sometimes that's looking at a three-dimensional structure, but then applying a line load across the structure, thereby recreating sort of what you consider two-dimensional loading conditions. So essentially, the sort of three-dimensional modeling approach also needed three-dimensional data to try and validate it against. And the majority of these structures were instrumented using LVDTs to get displacement measurements. And then for the UIC work that we did, we also instrumented with accelerometers. And again, I'll refer to that in tomorrow's presentation. So this is one of the structures here that we actually tested at quite high levels of loading. So with our other structures, they were all structures that were still in service, so we were restricted to sort of service levels of loading. This is a bridge down in Ballincollig, west of Cork City, that was essentially being taken offline by a new road that was being built. So essentially, this could be tested under higher loading conditions. So this was tested up as high as an 80-ton single patch load. So in addition to the sort of service levels of loading that we had to validate our models, we also had one example of high-level load tests as well. And we've also sort of tried to validate our models against sort of very simple things that are easily available, like crack patterns. And essentially, the aim with the modeling has been to sort of build up a fairly uniform approach to modeling arch bridges three-dimensionally. So this sort of refers to the sort of the modeling aspect of the work that's been conducted. We've looked at testing, we've looked at modeling, and we've looked at assessment practices and approaches. And that sort of work in UCD has been carried out approximately since 1999 up to about 2014, and has been variously funded by the National Roads Authority, the ICE, the EU, Dublin City Council, and the UIC as well. So with our finite element modeling, essentially it's a solid modeling approach that we take. And so we use solid elements, 8-noded brick elements for the masonry mortar continuum. So we treat both the masonry units and the mortar as a single continuum in the arch. And then the fill elements are also treated as solid elements. So that's sort of a key distinction between some of the other approaches where often the fill is treated as dead load and earth pressures, and with this we're actually sort of able to incorporate it as a solid element itself. And then essentially we have a frictional sliding contact between the fill and the masonry material, and this essentially allows the interface to stick and then slide once it reaches its limit. So typically, depending on the loading that we're trying to replicate, it's a multi-stage analysis that we take. The first step is to apply the self-weight. This is really quite important for assessing masonry arch bridges because you need to sort of lock in the compressive stresses into the arch. And it also becomes important because of the large mass that's associated with a masonry arch bridge when you're doing other types of analysis, dynamic analysis, for example, as well. And then essentially it's a series of iterative load steps, basically moving the position of the truck along the bridge. For our service load simulations to correspond with the testing that I'm discussing here, essentially that was all sort of carried out at quite low speeds. And so the approach that we've taken here is sort of basically a semi-static modeling approach where we're basically just incrementally moving the loads as opposed to conducting a transient analysis. So the material properties that we, and the material models that we adopt, we've kind of some typical material properties up the top there. So essentially you need a bit more in terms of your material properties to carry out these types of analyses. You need the stiffness, the Poisson's ratio of your masonry, its density, tensile strength, all sort of normal things, compressive strength. When you're looking at your fill, then you also need to have things like values for cohesion and your angles of friction and dilatancy. The model for the masonry and mortar continuum is basically a smeared crack model. And this is a type of model that was initially developed for looking at the ultimate capacity of nuclear pressure vessels. And essentially, what this will do is once you reach a limiting tensile value, you can specify what the tensile behavior is. We specify a elastic, perfectly brittle material behavior for our masonry. And once it reaches that tensile limit, essentially, you're reducing the stresses down to a very, very small value where they've occurred and redistributing them locally. You can't reduce them fully down to zero because it'll create numerical instability in your model, so it essentially gets reduced down to a very nominal value. With the compression behavior, we model that as elastic, perfectly plastic. As a number of the speakers have already sort of alluded to already, it's probably not really that important or significant because you're not really going to be reaching the compressive limits anyway. And so when we sort of do our ultimate capacity analyses and look at the maximum compressive stresses, they're really quite low and very, very far away from the estimated compressive strengths of the masonry we're considering. The fill material then is also modeled as a continuum, but we use a different material model. We use a Drucker-Parker yield criterion, which is essentially just a sort of an outer cone approximation for a more Coulomb model. And this is sort of just an example of one of the finite element meshes for one of the structures that we've done quite a bit of work on. So depending on our symmetry for our geometry and our loading, if we can, we'll do a half model purely just to save the computational expense. So because this bridge was nice and symmetrical, essentially we could just slice it down the middle. Obviously, we're trying to run our truck across it, so we can't actually cut it even further back to a quarter model. So it's sort of a half model approach that we're taking. Obviously, if you're looking at eccentric loading or your geometry is unsymmetrical, you can't take that approach, and you have to model the whole thing. And then you can sort of see down here some of the boundary conditions that we've applied. One of the big things that we sort of learned as the work progressed was initially we modeled the arches really sort of only about as far as the spandrel walls. But in effect, we were basically allowing the boundary conditions to interfere with the response of the arch. So in order to address that, essentially you need to ensure that you have a sufficient sort of approach length of fill so it's the fill stiffness that's dictating the response at the abutments and not simply a boundary condition such as the one out here. So we generally tend to use compression-only supports at the boundary so that your model doesn't hang off of its boundary conditions, and to basically sort of avoid tension at the edges. Essentially, you can see down here, this is basically the simulation of our service load testing that we undertook. So we had basically a double axle construction vehicle, which was heavily loaded, driving over the center line of the bridge at quite a slow speed. And then these are the locations of our LVDTs. So one at the crown, one's at the quarter point, one's at the abutment all along the center line, and then 3 out at the edge as well. So, sorry, this is just another one of the bridges that we modeled, and this is again just sort of illustrating the point that I made a moment ago. This was our initial approach, and then this was extending the fill out to the side so that we weren't artificially providing those supports at the abutment. So sorry, going back then to the first bridge that I was showing, these are the deflection measurements from our service load tests, and you can see in the line with the markers on it, that's our finite element simulation. So really not too bad at all. And these are at single locations, basically multiple passes of the bridge. So this one here is looking at the crown of the bridge, and this one is looking at the crown, but out at one of the edges. Revisiting again one of the points that has been made a couple of times today, this is basically looking at the contact pressures at our interface elements. And so you can see here, when the lead bogey is approaching the abutment, you have a nice, widely distributed contact pressure at your abutment. As it approaches the haunch, basically the front axle, you can see, becomes more concentrated, while the rear axle remains quite evenly distributed. And then as you approach the crown, really you can see that those contact pressures are becoming increasingly intense and concentrated. So in effect, when you're out at the abutment, and as you sort of approach the quarter span, yes, you're getting that nice distribution of loading that replicates the two-dimensional behavior and the approach that's taken to a lot of the load distribution models in relation to that. But you can see that it becomes increasingly invalid as you approach the crown. And taking a three-dimensional approach essentially allows you to look at the effect that has on the transverse capacity of your barrel. So the first thing that we did was look at the service load response. The next thing that we then did was to try and extend this up to the ultimate capacity load. So we started off essentially by applying a double axle load at the most onerous location. The way that we would identify that was essentially to just iteratively look at the stresses as you moved the bogey along the bridge, and they invariably were, most onerous positions were in and around the quarter or the third point for the bridges that we looked at. And essentially we then incrementally applied load at that location in 1 ton increments, factored out as it has to be in the codes between a heavier weighting on one axle than the other. So essentially we loaded it up in 1 ton increments up until what is basically the 10 ton allowable axle load equivalent, which when you factor it up gives you a total bogey weighting of 53 tons. And so we did this basically as our service load cycle. So we were basically loading it up to the maximum vehicle weight that you can drive over the structure. Again, this is just for road bridges. and then we ran it through 3 load cycles. And you can see that effectively, once you've gone through your first load cycle, the behavior is repeated. We then increased our load, basically looking at the different damage patterns and changes in stiffness as you approached your ultimate capacity load, until we reached an ultimate capacity load of about 104 tons across the double axle bogie. This gave us an equivalent allowable axle load of just over 19 tons per axle. So really quite a high load rating. Sort of our level 1 assessments, where we were looking at sort of our 2-dimensional elastic finite element assessments, were giving us load ratings of about 7.4 tons for the allowable axle load. So a significant increase in capacity, accounting for the transverse behavior, the effects of the fill, and also then the effects of the spandrel walls. This is the other bridge, Griffith Bridge, which was much shorter in span. It was also, it wasn't symmetric, so we had to model the entire bridge for this one. And again, just sort of looking at the correlation of our model with the deflection data. The lines with the markers are our FE model, and you can see that it correlates quite nicely when you're looking at the crown along the quite close to the center line. These are the predictions that were undertaken before the tests were actually carried out, and you can see that they match up generally quite nicely. The area where they didn't really match up so well is at the edges of the bridge, where really they were a bit overly stiff. And so the approach that we took was then to sort of assume that the spandrels have been damaged, and basically we preloaded them out near the spandrels to sort of create that level of damage. But in a sense, you're sort of guessing at that, and you're essentially, you're updating your model to try and match that loss of stiffness out at the edge. I'll skip through these because I can see that I'm running out of time. These are some of our high-level load tests, up to 60 and 80 tons. And then again, we sort of repeated the exercise of doing serviceability load cycles up to the 53 tons. With this bridge, we didn't get a repeatable response on our first couple of load cycles, and it actually took 5 load cycles in order to sort of stabilize the behavior. So we were essentially getting progressive cracking on each load cycle that you can sort of see illustrated up there. And essentially, when you brought it just a little bit beyond this, you got another change in stiffness. So effectively, we were operating quite close to that level. So we were sort of getting incremental damage as we approached it. Again, we tested it, or we simulated it up until failure at a total of 167 tons. But effectively, you can see that the damage is occurring at a much lower level load, at a much lower level than the 50% that Bill mentioned earlier is in the codes, and you're also getting different changes in stiffness as you look at that response. So this table here just summarizes the results for a couple of the bridges that we went through this process with. And there's lots of numbers there, but effectively what we've looked at and what we've classed is what level of loading the initiation of damage occurred at, what level of loading the change in stiffness occurred at, compared this with the legal load limit, and what the ultimate capacity we predicted was. So your initiation of damage and your change of stiffness is essentially occurring at a much lower level of loading than 50%, often around 30%. And essentially, really, it's trying to address the question of if you have an ultimate capacity assessment and an ultimate capacity load, how useful is that to you if your bridge is deteriorating when it's operating below that load? And so essentially it's trying to develop a tool that can investigate that a bit further, look at your specific damage patterns that it's experiencing, and try and predict what level of loading will actually cause damage and will actually cause a change of stiffness in the structure. And I think that I will leave it at that. Okay.